All right, grade 11. Today we're doing lesson number 6, graph types and reading graphs. Now, I think most of you know the different types of graphs, but we're not really great at picking the best graph yet, or even setting those graphs up particularly well to be very clear and convey the most information I possibly can about your data set. So we're going to work through this today, and we're also going to look at some examples of graph analysis questions that have shown up on old IB exams, paper 2 and paper 3. So first thing, hand length. If you did not finish that data collection and analysis before you, for last lesson, you're welcome to hand it in for this lesson as well. So we have to have the descriptive statistics, mean, median, mode, and range, and then after today's lesson, you should be able to also add how you would graph that hand data, and if you added the age, how would you graph age and hand length? Okay, so keep that in mind, and we can upload that as part of today's lesson as well. Okay, so the types of graphs. So for this course, the IB has specified 4 different kinds of graphs you have to be able to make and analyze, and these are most common ones used by scientists. So those would include bar graphs, right? So here's my bar graph. It would include line graphs like this, scatterplots with a line of best fit like this, or even without line of best fit, and then histograms like this kind. Okay? I notice a lot of you guys on your labs tend to automatically go to a bar graph, and that is not very often the best graph choice for scientific data. Sometimes it is, but most of the time it is not. So choosing the right type of graph for your data is something that a lot of students struggle with, and your cohort is no exception to that rule. We're still working on building that skill set. So why do you think it's so important to pick the right kind of graph? Well, if you want to, the purpose of a graph is to communicate the trend in your data. So what did I see? What did I learn? What does it mean? And if you don't pick a graph that clearly shows that trend, that shows that information, then what is the point of having a graph? Right? You need to not think of the different components of a lab write-up as check marks on a list to accomplish. You need to think of them as what their purpose is in communicating what you found, what you did, what your plan was. Because every part of a lab write-up is designed that way, to give a comprehensive examination of all the components, what they mean, and what it can tell us. Okay, so let's start by talking about line graphs. So here's 2 examples of line graph. Here's one from the earlier example. We have the months, the year, and some numerical value that's not labeled, and this is an old IB exam question. So a line graph is going to plot single points on a Cartesian plane. So each x value has only one corresponding y value, and that's a key part of a line graph. And we join those points by sum to the line, straight line. This is forming a curve or connecting those points to the line because it is continuous data. So usually the x-axis is the independent variable and the y-axis is dependent variable. Hopefully you've already noticed that. So if you notice here, amount of salt in the soil related to time. Time is almost always on the x because of the independent variable. Right? I think time is independent, I think time is time. Whereas the amount of salt depends on time. Okay? So when are we going to use a line graph? Well, line graphs are most often used when we have variables that are quantifiable. Both variables have to be numerical in their form, and they have to be related and not discrete. So each variable has to be connected some way. If they're not connected, we should not join them in a line, because they're not separate individuals. This is one individual, or this is a mean in a data set. It's something like this. So a change over time is a really clear and logical one to use a line graph for. So we have salt and soil over time. That's a good one to use a line graph for. We have months, the year, and some variable here, another good one to have a line graph for. Maybe this is population graphs. I don't know. Okay, it's line graphs. Bar graphs. Bar graphs use rectangles to show the amount of data within a category. So in this case, we have categories, and then we have numerical data. So it's a little bit different. This one we have 2, this is numerical data here. So your y-axis is quantitative, and you can have more than one. So this can be a good way to put more than one graph together is by having two different y-axis and using color. This is from an old IB exam. The x-axis, though, is qualitative. It's some sort of qualitative value you can describe with a name. So here's different chemicals, here's years, that kind of thing. It could be gender, it could be descriptor, it could be color, whatever it happens to be, but some sort of qualitative value. There's not really a rule to the order of the bars. If you're doing years, it should be in chronological order, but most of the time you won't be doing years for this kind of graph. You'll be doing, yours should probably be a line graph is better. But you'll be doing here showing the order of these makes no difference as far as the trend being conveyed. Now it makes a lot of sense to put the control first so you can compare everything to the control, but the order of these really does not matter. If you want to put in the order that you did them or alphabetical order, it doesn't really matter. The information will stay the same. It will not affect the trend you're showing. So what kind of data would you show in a bar graph? Well, it's going to be something with a qualitative component for sure. It has to have qualitative or there's no reason to use a bar graph. And then a qualitative with a quantitative that you want to compare. Most of the time, it's not the best graph type to use for science. Most of the time in science, we have two quantitative variables, and therefore bar graphs are not great choices. But I see a lot of them in student lab reports. I don't know where you guys got your fondness for bar graphs, but please don't pick them just because you think they're easy or you're familiar. Pick the right kind of graph for your data. Okay, next one are scatterplots. So scatterplots is when you have two variables, two quantitative variables, and they can be plotted along XY values. They have to be quantitative. So here we have a sales price and we have square footage. And here we have clearance rate and larval stage. And this is also from an old IB exam. Okay, these are really useful when you have one X value, like one square footage area, or one larval stage can have multiple Y values. And these are used very often in science when you have multiple subjects or multiple trials to compare into a single graph. This way you're not comparing a mean, you're putting all the data there and then you can use a line of best fit to compare them. Okay, sometimes you use a line of best fit to help compare and see the general trend or maybe a regression line in your data, but you never, ever, ever connect these points because these points are not related. Like this is not a graph of the same apartment's value changing over time. That would be a really good one for a line graph. These are different square footages and their prices. These are all different buildings. These are not really, they should not be hit by a line. The line of best fit can help you see the trend, but it's not connecting the points. Here, there's not even a line of best fit, but you can kind of see a relationship is looking like this. Okay? So when might you use a scatter plot? Well, scatterplots are super useful in science because a lot of the time we have multiple trials. It has to be a case where we have both variables are quantifiable and the trials are not related. So if you're comparing different individuals, the same kind of data set, you're going to use a scatterplot. So anything like we did our ventilation rate lab, practical 6, you're comparing ventilation rate before and after exercise for different people, scatterplot would have been a great graph type to use because you could plot all the different people's, let's say one individual's mean ventilation rate after exercise. You can plot that for every single individual in that study. I think we had like 40 some people. All of them could be on that scatter plot and you can really get an idea for the trend in that data set. It's a very common one to use in biology. Okay, and the last one that I want you to know about are histograms. So histograms use rectangles for the data, like a bar chart, but the difference here is the x-axis is a quantitative scale. So these are not going to be categorical like they are in a bar chart. Okay, so we have some sort of quantitative scale that has intervals of continuous data. So age is a good one, a very common one to use in histograms. You might see time, those kinds of things. Grades in school, something like that. It's going to be continuous over time. You'll notice here that there's no space, no gaps between the different histograms because it's showing it's continuous over time. Here, because they have more than one thing being shown, they have the dark and the light, put a tiny space between. It's a lot smaller than it would be with a bar graph because we're trying to show the continuous nature of this data. In this case, I believe the light gray one is the mean, and the dark gray one is the total age range. Okay, now the width of the rectangles is an incremental value. So this is incremental of 10 years, each one here. These are also 10-year increments, and they have to be in that particular order. Okay, so we have to show this continuous. It has to be, you can't put the 60, 70-year-old bin over here between the 30 and 40. It's not going to make sense. You have to put it in the right order based on the sequence you're choosing, based on whatever data you're showing, because the data is continuous. Sometimes we call these little rectangles in a histogram, we call them bins. And basically you can think of how many people or how many subjects, how many data points fit into that bin. So how frequently is a 20 to 30 falling into that bin of whatever it happens to be. Maybe this is people who have hands bigger than 15 centimeters. How many people in this age group, that age group, that age group, that age group fit into that category? Okay. So what kind of data do you display in the histogram? Something where it's a continuous, one variable is a continuous data point, like age is a really great example. And the other variable is showing frequency. You want to see how something affects age or how age affects something else. That could be a good one to use, because you can have whatever variable you want here on the side and just show the frequency of it in this data. Okay. Okay, let's talk about regression. Some of you have already been using regression. I know it's taught in the 10th grade in math, so you should be very familiar with this, but I want to review it in the case of context for your IA. So linear regression is a tool we use to examine linear data sets. So the data has to be linear, otherwise regression is not going to be helpful to you. Okay, that's the first thing. Is my data linear or not? So the regression line is a straight line that is as close to all the data points as it can possibly be. So if you're doing this by hand, you'd put a ruler down and try and make it so that way all the points above on top and the points below make it equal, so that way if I was to add up the distance between each point and the line here, and look at a negative value, this is -1, -5, -15, whatever it happens to be, and add up the positive values here, how far away from this point, it would equal 0. So this is close to, it's exactly between the top and bottom values. The easiest way to do this is almost any computer software. You make a scatter plot, put a line of best fit, put linear regression, it'll do it for you. The really useful part of this is we then click R-squared value. So here's the R-squared value for this data set, 0.702. And what R-squared is, you have to be careful with this. A lot of students just think it means how reliable your data is, but it's not really that. It's how much of one variable's variation, or let's say the x value variation, can be explained by the other value's variation. So how much does this variable, does the y value explain the x value? So these points, how much of where that point is explained by this point? How much of the value of this is being like, what, 28 is explained by the fact that it happened in 2003. Okay, so you can think of it as a sum up to 1. So if the R-squared value is close to 1 or -1, the more strongly correlated those two variables are going to be. So this one is 0.702. It's pretty close to 1. It's not great. Like anything 0.8, 0.85, 0.9 is better. And often if you have more data points, you're likely to get a better R-squared value. That being said, this can be a really good measure to check out if your data, if you have sufficient data, if you're seeing a trend in your data for those particular variables, especially if you're doing more than one dependent variable and you want to look at which one to pursue further. You can do a quick graph of your data and then see what the R-squared values are. If they're good, you can keep pursuing that particular data set. But this is not sufficient statistical analysis. Okay? Up till now, I've been pretty lenient because we haven't talked about this kind of stuff in class yet, so I wasn't going to hold you accountable for it. Some of you guys went ahead and learned for yourself, which is great, but I'm not forcing you to do statistical analysis for your labs. Now we're starting. Okay, so you're welcome to do regression. I encourage you to do it, but it should not be the only test you do. Okay, so when you're making a graph, you have to make sure the graph you made actually is useful. The number of times I've graded a student's lab report and they're missing information about their graph and therefore the graph means nothing to me, if I had a nickel, I would be retired by now. It's a shame because it's a small thing that you forget to do. It's not a blaringly obvious thing, but it really makes your data useless. So you need to make sure for your communication grade and for scientific communication in general that your graph, every single graph you use, has a clear title and labels. So your labels for every axis need to include the units and a clear scale. If you do a graph digitally, they'll do that for you, but you need to include the units here. Okay, so here you have CO2 emissions in metric tons. They have the units there. Okay, your title should be detailed enough your graph can stand alone. You shouldn't have to read the text before or after your graph to make it make sense. It should be enough to make it stand alone. So try and make a title for this graph here. So example of a good title for this graph would be the change in carbon dioxide emissions measured in metric tons in 4 European countries from 1967 to 2007. Very clearly saying exactly what that is, which means I can look at that graph with that title without being in a lab report and it still gives me useful information. Okay, it doesn't have to be in the report to be useful. It should be able to stand alone. Okay, and then oftentimes, something I noticed with you guys, and a lot of my students in particular, at this school really, is that people tend to put like 5 or 6 graphs and a single data set on each graph as if like that's a better way to communicate their data. But the point of a graph is to create the trend in your data. That means comparing the different data sets. So doing that where it's all in a single graph multiple graphs, means you have to scroll up and down the pages, flip the page over, it's printed on paper to see the different values. If I look at this graph, I have 4 different data sets on a single graph. This means I can really easily compare the fact that the UK has been going down over time, which you can see by itself, but it was above Sweden's peak. It was still much higher. It was still higher than that. It never got above the UK's values. I see the UK's final value is still higher than all the other countries. I can see that Sweden went below Italy and just below Portugal. So I can compare them in a way that I can't if they're on separate graphs. Think of these data points as, if they were on 4 separate line graphs, how much less useful would that be compared to this? Okay, notice how the key here, they've chosen to do dotted lines or dashed lines for the graphs they're going to overlap, and then since they don't overlap, keep them a solid line. That's a great idea. It's even clearer to the trend in these ones which are dashed over as it goes behind the blue and the yellow one. They have the key right beside. Color is really helpful for making things in graphs. You'll notice in the different IB exam questions are never in color, and sometimes I really wish they were because it would make things clearer. But your IA can totally have color graphs to help make things clearer for you and the person grading you. Okay, so remember for hand length, do the descriptive statistics, mean, median, mode, and range. How would you graph the hand length data? If you added age, how would you now graph hand length and age? Okay, and go from there. All right, let's talk about correlation versus causation. So correlation is the relationship between 2 variables such that when one changes, the other does also. So these 2 are changing either in opposite or the same way. If they change, both when one changes, the other changes too. Okay, so in this cartoon, which 2 variables are correlated? That would be sales and shaved heads. So, and correlations can be positive or negative. So what does that mean? Well, these 2 are positively correlated. As one increases, the other increases. They can be negatively correlated too, where if one increases, the other decreases. As long as one changes, the other changes, they're correlated. Now, if you notice this cartoon, this guy's taking this correlation and saying, all right, guys, everybody grab a razor. Okay, so based on the context of this cartoon, the statement correlation does not equal causation. What does that mean? Well, just because people with shaved heads tend to have higher sales does not mean that shaving your head causes you to have better sales. So if these salespeople all shave their heads, would they automatically become better salespeople? Probably not, definitely not. What's more likely is some other variable is causing this correlation. Something else increases both sales and shaved heads. To my mind, something that makes sense for this would be confidence. If you have somebody who's confident enough, male or female, to shave their head, that's a really confident haircut to go for. And confidence is also an important trait in salespeople. If someone's confident, they're going to be able to convince you to buy something more better, you're going to believe them, all those kinds of things. So probably an exterior variable is causing this pattern. They're still positive correlated. So be really careful when you're talking in your data that you don't think that just because something is correlated, it's actually causing something. Be very, very careful about that. It can get very tempting that you think something's causing the other thing. But just because there's a correlation does not mean there's causation. Here's another example. I actually saw this for the first time in the statistics research department I was in grad school. I worked for a research organization there. And I literally stopped in the hallway after one shift and just started laughing so loudly it was kind of embarrassing. But I was really tired. It was really funny. So take a look. If this doesn't make sense to you, then you need to go back to this slide and listen again. Okay, so the idea here needed is that this person's implying that the stats class helped them understand the difference between correlation and causation. But this person now knows they're not the same, so maybe it did, but we can't say for sure that the stats class caused this learning, because that would be implying that correlation caused causation. Just because increased knowledge of statistics also increased the understanding that that correlation does not cause causation doesn't mean that that caused it. Anyway, that's really poorly explained, but I find it hilarious. Nerd alert. Okay, so let's talk about different types of correlation. So these are good terms to be using when you're talking about relationships and graphs, and that comes up a lot on IB exam questions, paper 1 and paper 2 and paper 3. So as we have positive correlations, we have negative correlations. Okay, so positive as this variable increases and this variable also increases. As this one increases, that one increases. Negative, as this variable increases, that variable decreases. And then we have the strength of the correlations. Really strong, things are really close in a very linear model. Weak, there's some linear there, but it's not super strong at the beginning. And then we can have a moderate correlation where things are following the line better than this, but not nearly as good as this. And of course, you can have no correlation. And that's valid to say as well, there is no correlation between these two data points. Okay, so now we're going to look at some examples of graphs from old IB exams to practice this interpretation skill. So first, take a look at this graph. Look at the level of detail in this graph. What is here to help you interpret it? Well, there's a very detailed title. Look how detailed this title is. You can read this title and look at this graph and not need to read anything else to be able to understand what it's showing you. Your titles should look like this. Okay, both axes are very clearly labeled with the units. There's a key or a legend because there's two different data sets here. And then the question I'm asking you here is to describe the trend. So look at the Woods data and the Fields data, the X's and the O's, and see what you can find. Pause the video and try it yourself. So you should notice is that in the Fields data, the little X's, so the little O's are the Fields data. That graph, those data points are mostly over here in the Scatterplot, and this is where I would wish the IB would use color. So these were different colors, it'd be much easier to see, in my opinion. Most of them have much higher values on this axis. So we have from like 50% up to even 100% of yellow base color shells. So most shells in the woods are yellow base color. Whereas in the woods, we have a lot more over here that are much higher percentage of being unbanded. Now we do have some ones over here that are kind of outliers. We have some over here that are unbanded and 50% yellow. And there's ones we have really low amount of yellow, mostly I would say probably brown, okay, or other colors besides yellow, but most of them are not banded, or most of them are banded for the woods, but most are not banded for the fields. So this kind of interpretation is what you're going to have to do paper 2 and paper 3, and you can expect to see more of them on your unit test from now out. Here's another one. So take a look and describe the trend. So the actual intake is a mean value and recommended intake of fiber, males and females in different ages. So you'll notice here that males are supposed to intake more fiber than females, and they tend to take in more fiber than females, but much less than they should. And I would say the females in the middle kind of age groups here, I even say more specifically from ages 30 to 39, the females definitely take in closer to the recommended intake than the males in 30 to 39. Right, you can actually read the numbers off a scale be best. I probably would use a ruler to help me line those things up. But they would like you to talk about specific data points in your answers. Okay, here's another one. So here we have salt buildup in soil, and we're showing the effect of bacteria over time and the amount of salt. So these salt metabolizing bacteria being added to the soil. Okay, so outlining the trend, as time goes on, the amount of salt in the soil decreases, and then kind of plateaus. It begins to decrease very quickly, and then continues to decrease at a much slower rate. Okay, here's another one. We've got 2 scatterplots here showing starch and fiber intake and colon cancer. So what's the relationship between fiber intake and colon cancer mortality? So I'll be looking at this graph here. It's a negative correlation. So as fiber intake increases, colon cancer mortality decreases. And then determine the predicted mortality due to colon cancer at a daily fiber intake of 12.5 grams per day. So at 12.5, what's my colon cancer mortality? About 16.5%. Okay, here I have that double y-axis graph about citric acid. So take a look and answer the question. Identify the nitrogen source that results in the highest yield of citric acid. So my highest citric acid is going to be my dark gray box I'm looking at, and the highest number is here, NaH4NO3, ammonium nitrate. Okay, looking at day length and biomass of algae over the course of a year in the habitat of Daphnia. And Daphnia are very tiny organisms that consume algae. So identify the month during which the quantity of food is at a maximum. So my dark line is algae, so the maximum algae here is between April and May. And then compare the changes in biomass of algae with the changes in day length from January to June. So I'm going from January up here till June here. So just this part of the graph. Oftentimes the IB will only ask you to look at one part of the graph, and students sometimes will talk about the entire thing. Don't do it. Focus on what they actually focus on. So January to June, here we go. So as day length increases, the algae population increases, peaks, and then decreases. And so by the time June hits, the population is quite low and then starts to increase again. This is probably because it reached carrying capacity, outcompeted itself, ran out of resources, then plummeted back down again. And you should be setting actual data points, right? So from January until April, the population was increasing, and in April the population peaked, as day length was still increasing continually up until June. It finished increasing. Then the population of algae decreased in in May until June, and day length was still increasing, and then started to increase again the biomass population. So that kind of thing, using actual data points, and you should put numbers here that reached a maximum of about 17, just arbitrary units, no real units for biomass. When the day length peaked at 16 hours in June, when the day length was at 14 hours, the biomass algae peaked at its highest value, that kind of thing. Use actual data points to help. Okay, so here's another set of graphs. Here's scatter plots talking about different larvae. So we again have two different symbols. So we have the circle are the larvae with high food availability and the line with low food availability. Okay, so the clearance rate they're showing is indication of how quickly food can be digested and used for growth. And graph 2 is showing the tentacle diameter as a way of measuring larval development. Okay, so the bigger its tentacles are, the more developed the larvae is. Okay, so what's the relationship between low food availability and tentacle diameter? So we're going to look at tentacle diameter over here, and then low food is the little dashes. So what we can see here, it's not up to a maximum of 200 microns is the maximum tentacle diameter with low food availability. Nothing gone beyond that limits tentacle diameter. You could say it's limited tentacle diameter, it's not going fully developed. And you have the smallest is 48 or so microns, something like this. Okay, so here's more graphs where in this case you'd have to actually be doing some calculations. So here are ventilation rate graphs. So we're seeing the volume of liters of air being taken in before and after exercise. And you'd actually measure and calculate the rate here. Okay, and here's another interesting one. This is a unique question. I've never seen anything like it repeat itself. But it's showing the movement of the American cockroach. Their antennae are very, very sensitive to touch. And if you touch the antenna, it will cause it to immediately turn and run away. So they did a bunch of touch trials on cockroaches, which I hate cockroaches, they're so gross. Most insects do not bother me, but cockroaches for some reason, well. Anyway, so here we have the symbol showing the orientation of the cockroach in figure A. And the circle was the head of the cockroach. So if it tapped on an antennae, then they plotted its movement. Okay, so here's a path of the movement of the cockroach. And then in figure B, we have the initial angle of the cockroach's turn when tapped on the left antennae. So we tap them on the left, which way they can turn. Most of the time they turn away from that stimulus and over here, which makes a lot of sense. They're running away from whatever stimulus it happens to be. And the arrow is the mean angle. And here is our histogram showing the response time between the touch and action for 215 trials. So how often did they move within 20 seconds? Like 26 or 27 times, they moved in 20 seconds, then breaking it down even further just into, it's like every 2-second intervals. Okay, so you describe that trend is that most of the time the cockroaches moved away from the stimulus, would be one trend you could say. You could say that most of the cockroaches' response time was between, was it 20 was the most, and then 24 seconds, 20 seconds, 24 seconds the most after that. These are the kinds of things you can say, but cite specific data points. And this skill set, you'll never probably, no one ever saw this graph, this kind of data probably before they saw this question. What the IB wants to know is, can you see a graph, read the titles, read the information, and then interpret it? Do you have that skill? It takes practice to get there. Okay, so your homework, upload your notes from today's lesson. Make sure in the split page you're commenting, okay, what kind of graphs would work for my IA? What should I be doing for my IA for that? Make sure you also include the analysis for hand length data, right? Mean, median, mode, range, the graph type, and the graph type for hand and age as well as just hand length. If you haven't already, make sure you're deciding your IA topic with me. Your final topic is due on Monday, and I have to approve it. All right, guys, that was a long one, but hopefully the practice questions will help you get better with your graph interpretation and choosing the right graph.